So to start with, let's show that we can build a finite state automaton for the empty string. Do that with your neighbors. Build me a finite state automaton for the language of just the empty string. Yeah, in the back. So here we have the start state, which is also a final state. That is this first one here. And then on anything in the alphabet, we're going to transition to maybe some trash state. And then the trash state transitions to itself on anything in the alphabet. So the only way that this machine can return 1 for anything is when we don't take any transitions. And the empty string is the only string that doesn't take any transitions. Okay, so we can do the empty string. Any regular expression that is just the empty string, we can certainly now make a finite state automaton for that regular expression. So we have one case down. Let's do more cases. Show that if I have a regular expression that is just a literal character, show that I can build a finite state automaton for that regular expression. Do that with your neighbors. I'm going to call the literal character X, just for clarity. Yeah, go ahead. So this is saying that we start in the start state. If I get the character I was looking for, then you go to that final state. If I got anything else from the start state, so this is saying if the character I got was anything from my alphabet except for whatever X was, then we're going to go to trash. And once I was in that final state, if I got anything else, then I was going to go to trash. So the only string which will cause this automaton to end in its final state is going to be just the string containing X. So no matter what literal character we had, we can build a finite state automaton for that. So we kind of have our base cases. These are sort of our 2 base cases for this proof by induction that we're doing. By the way, I don't think I ever mentioned what kind of induction this was. This is typically called structural induction. The idea behind that phrase structural induction is that we're saying that the thing that we're building has some sort of structure to it, and you build upon this structure using certain rules, and you're showing that you can build anything because you can just use those rules, basically. So you just show, since you can do any of the rules, that means you can do anything that you could eventually build. You have a question? Yeah, so we're sort of going to be able to allude to them in some sort of abstract way, if that's what you mean. We can just sort of say, invoke the literal character thing here, for instance. Kind of like what we did with syntactic sugar. So you can think of this as building up some finite state automata syntactic sugar as well. Okay. We've shown that if I have a really, really simple regular expression, I can convert it into a finite state automaton. Now I'm going to show that if I have 2 simple regular expressions, which I can represent with finite state automata, then I can build a new finite state automaton to represent the alternation of those 2, or the union of those 2. So in order to do this, basically what this question is asking is computability with finite state automata closed under union? It's asking us to show is computability with a finite state automaton closed under union. That is, if I have 2 languages, let's say language 1 and language 2, and I knew that both of those 2 languages could be computed with a finite state automaton, I want to know, is the union of those 2 also going to be computable with a finite state automaton? So when we looked at the definition of alternation up here, when we do the alternation of 2 regular expressions, that'll match strings that match at least one of the 2 parts. So it says we can match the first part or the second part. In other words, the set of strings that will match is the set of strings that match the first one, union the set of strings that match the second one. That's why we called this union. So if I can show that computability by finite state automata is closed under union, then that means that I can take 2 finite state automata representing regular expressions and create a new finite state automaton representing the union of those 2 regular expressions. Doing this is actually somewhat tricky, because we've kind of got 2 machines. So I've got 2 automata that I have to deal with. Let's say M1 is whatever is the finite state automaton that computes language 1. And M2 is whatever finite state automaton computes language 2. If I'm trying to create some new finite state automaton, let's call it M sub union or something like that. if I'm trying to build some new finite state automaton that's going to compute the union of those two languages, this finite state automaton needs to return 1 for any string that M1 or M2 returns 1 on. That's what this machine is going to need to do. It's going to need to take some input string, and it's going to return 1 or 0, return true or false for that input string, whatever it is. And we need to design this M union in such a way that it's going to return 1 whenever either M1 or M2 returned 1. It's going to return 0 whenever both of them return 0. So it needs to somehow play the role of both of these machines. So whatever it's doing, it needs to be able to play the role of two machines, but our model of execution for finite state automaton said that we can read the input how many times? This M union that's going to be computing the union of those two languages, it needs to be able to, by reading the input just once, figure out how both of these other two machines are going to answer. So that's the challenge here. We need to build this new machine M union that is going to end in a final state, where for some string it'll end in a final state whenever either of these two machines did. It will end in a non-final state when both of these two machines did. And it needs to be able to answer that question by reading the input just one time. So this is the challenge. Do we understand why, if we can do this, we can compute union? So the way that we're going to do this, so if you'll recall from last class, we had this example where I said, here's a finite state automaton for AND. Can we make one for NAND? And the way we did that is we basically said, well, AND is the complement of NAND. So AND and NAND are complements of one another. So what we can do is we can just say, if I have some machine for AND, I can build a machine for NAND by just saying, I want all of NAND's final states to be the non-final ones from AND. We can sort of apply this idea to, in general, doing the complement of languages. Or we could say, if I've got some finite state automaton, let's call it M, that computes the language L, then this finite state automaton is going to compute the language L complement. Where this finite state automaton is exactly like the one we saw before. It's got the same states, the same transitions, the same start state, and so forth. The only thing that changed was which states were final, which is the opposite states that we had before. So in general, what this is saying is that whenever I can compute some language L with a finite state automaton, I can compute that language complement with a different finite state automaton, guaranteed. And the reason I know that I can do this is because whatever finite state automaton it was that computed L, I could use it to build a finite state automaton for L complement. So I can, by manipulating that finite state automaton that I assumed exists, I could build this new finite state automaton for L complement by saying, just do the same thing, but invert the roles of the states. So that the final ones are non-final, the non-final ones are final. So that says that whenever a finite state automaton exists for L, there also exists one for L complement, and I know that because I can build one using the one that L had. This is in general how we go about showing the closures for this computability with finite state automata. Is we say, assuming that we start out with things with finite state automata, if we wanted to do this operation on the language, we can manipulate those finite state automata in this parallel way in order to guarantee a finite state automaton exists for the resulting language. So here we said we have the complement operation we want to do on languages. This inverse the final states operation does the same thing to the automata, basically, as complement did to the languages. So our general strategy for computing union, then, is we're going to say, assume that I have finite state automata for language 1 and language 2. Let's call them M1 and M2. I want to know, whenever there was a finite state automaton for language 1 and language 2, was there also going to be a finite state automaton for language 1 union language 2? Provided one exists, I'm going to end up calling it M sub union. So our idea is we want to build this finite state automaton that can sort of play the role of both M1 and M2 while reading the input sort of simultaneously. So our idea is that this one finite state automaton is going to simulate both of these other two at the same time. So if I can build one finite state automaton that can sort of do the same thing that two might do at the same time, then that's going to be what gives us now one finite state automaton for the union of those two languages. So let's look at an example of what it is that we're trying to do here. So let's say that I wanted to compute the union of this AND language with the XOR language. I want to compute the union of AND with XOR. First of all, who can describe what the resulting language is? It's the result of the union. What things are in the union? Yeah, so all strings that have only ones in them, or they've got some zeros, but there's an odd number of ones. These are two automata for those languages. This left-hand side automaton, this is an automaton for AND, this is one for XOR. I want to be able to do the union of this. And in order to do the union, I want to have kind of one super automaton that can do the same thing as both of these other two. So for instance, who can give me some string that they want to put on this automaton? Just any string at all. 1, 0, 0, 1. Okay. I'm going to sort of step through the idea for what we'd like this super automaton to do using this string. Okay, so the super automaton, it's trying to do whatever both machines did as the one automaton. So that means that instead of being in just, say, one state at a time, it's going to be in two states at a time. One state from the AND machine, one state from the XOR machine. Its current state is going to be which state the AND machine is in and which state the XOR machine is in. Where are we when we start? Before we read any characters, where are we when we start? We're in start in AND, and even in XOR. So this super machine, whatever it's going to do, its start state is going to be representing AND being in start and XOR being in even. The next thing we're going to do is we're going to read a 1 from the input. Where is AND going to be when we read that 1? Yeah, so AND is going to be in no zeros. Where is XOR going to be? Yeah, XOR is going to be in odd. So now we've read that 1. Next, we're going to read a 0. What happens after we read that 0? Where is AND going to be? Yeah, so we're going to be in some zeros, because we were in no zeros before. We got a 0, so we're going to take that transition up to some zeros in AND. Where is XOR going to be? Yeah, stays the same. So XOR is going to stay in odd, because we were in odd, we got a 0, so we took that self loop to end up at 0 again. So now we've read that, and we're going to get a 0. Where is AND going to be on that 0? Some zeros still. Where is XOR going to be on that 0? Still odd. And so we've read that, and now we're going to do that final 1. So on that 1, where is AND going to go? Some zeros. Where is XOR going to go? That's going to go to even. So we end up in some zeros as well as even. So should we return 1 or should we return 0? Both of them were non-final, so we return 0, which is what we wanted to do. So this is the behavior that we want this union machine to have. To be able to sort of do what both machines are doing sort of in lockstep on that same input question. That's correct. If exactly 1 was in a final state, we'd want to return 1 here. If both of them were in final states, we'd also want to return 1. We want to take one input character at a time and sort of transition in both machines in lockstep. That's what we're going to want this union machine to do. So we're going to build a union machine that's going to behave in that way. Where the way we're going to do that is we can take this machine, and this machine is going to have one state. So this union machine will have one state to represent every possible pair of states in the original machines. So each possible pair of states in those original machines, we're going to represent as a single state in this combined machine, so that by transitioning among these super states, we're kind of simulating working in both machines simultaneously. If we look at our AND machine and our XOR machine, this is going to be our union machine over here, where in this case we end up with 6 states in my union machine because I wanted every possible pair of states from AND and XOR. There were 3 in AND, 2 in XOR, so the product of those is the number of ordered pairs we could have, so we end up with 6 states over here. So now each of these states is representing being in some pair of the original 2 states. Which one should be the start state? Yeah, so start and even, that's the one that should be the start state, because that was the pair of start states from the original machines. If I'm in start even and I get a 0, where should I go? So where does the AND machine go on a 0? So the AND machine on a 0 goes to some zeros. So that means I need to be going to one of these 2 states for sure. To figure out which of those 2 states I want to go to, I want to figure out where XOR goes on 0, which is back to even. So on a 0, start even goes to some zeros even. Where does start even go on a 1? So it goes to no zeros odd. So on a 1, start even goes to no zeros odd. If we're in some zeros even, where do we go on a 0? So some zeros and even. On a 0, some zeros goes back to some zeros, even goes back to even. So some zeros even goes back to some zeros even. On a 1, where does some zeros even go? So some zeros even goes to some zeros odd on a 1. And we can repeat this for kind of all of these pairs. Which ones are final states? Yeah, so anything that had either or at least one of no zeros or odd is going to be a final state. Yeah, or start. No zeros, odd, or start. So start even, that has start in it. So that's a final state. Start odd, that had start in it. So it's a final state. It also had odd in it, which would be enough to make it a final state. Some zeros even is not a final state because neither some zeros nor even were final states. Some zeros odd, odd is a final state, so this one should be a final state. No zeros even, no zeros is a final state, so this one should be a final state. And then no zeros odd, both are final states, so we want this one to be a final state. Questions about this? Yeah, in the back. No, you would not. So if you want to see it completed, there it is completed. Notice there is no possible way to use this start odd state up here. We can still have it in the automaton if we can't reach it. It doesn't harm anything. It's certainly unnecessary, but it's not actively harmful to our automaton to just have it floating around there. It's even fine if we make it a final state. We can never get to that final state in order to return 1 for some string that took us there, but that doesn't mean it can't be a final state. It just is useless. Yes? Yeah, I got lazy and sort of gave up just to make it clear that we couldn't actually get there. To make this actually properly satisfy the definition of a finite state automaton, you would have to have the outgoing transitions from that state, but there aren't going to be any incoming transitions to that state because it's impossible to get there. That is a very good point. Okay, so this, by the way, is typically called the cross-product construction. The reason it's called the cross-product construction is because in the machine we created, the states were pairs of the original state. So our state set over here is the cross-product of the state sets over here, or the Cartesian product, if you prefer that terminology. So we typically call this the cross-product construction for automata, and it essentially allows you to have one automaton that does the transitions for 2 machines at once. Or you could do triples and do it for 3 machines, or quadruples and do it for 4 machines, and so forth. So in general, if you want to see this in super hard to read notation, because why wouldn't you? If I have this machine 1 that is defined as such, where I've got my states, I've got my alphabet, I've got my transitions, I've got my start state, and I have my finals. And then I have the same thing for this machine 2 over here. I can build this union machine by saying my state set is ordered pairs of the original state sets. My alphabet is the same as what the other alphabets had. I've got some sort of special transition function that I'm going to talk about next. My start state is the pair of start states from the original machines. And then my final states are defined down here, which is any state where one of the two things in the pair was a final state. And how does our transition function work? So if I have some pair of states, Q1, Q2, and I want to transition on some character, my next state should be transition using the first function on the first state, transition using the second function on the second state. So this is super formally with notation what cross product is doing. If you sort of understand what this is doing less formally, then you're totally fine on that. But that's what it looks like if you want to do it purely with notation. Yeah. Yeah, as long as you're consistent. In this case, the order does not matter. So the cross product construction, we can actually do other operations, for instance, intersection, using the same technique of this cross product construction. For different operations I might want to do, the order might matter for those. For union, it does not. Question. Typically, we just sort of say the alphabets are the same. We kind of say we pick our alphabet in advance, and then we start talking about some languages, is usually what they do. If they're different, then you would say that the alphabet for the union machine is the union of the alphabets. And you would end up with, it would be, weird things would happen. So we're just always going to assume the alphabets are the same. How would this change if I wanted to do intersection? If I wanted a machine for intersection, how would this construction change? Yeah, go ahead. Yeah, so for union, we said that we wanted to return one, or we wanted our final states to be those where either state in the pair was a final state. Because we said we wanted to return one whenever either machine returned one. If we did intersection, then we only want to return one when both machines returned one. So our only final state, if we wanted to do intersection, or our only final states, plural, would be this one, and then our nonsense one. So if we wanted to do intersection, those two would be our final states. Because those are the only ones where both states in the pair were final states. So this cross-product construction is generally useful whenever you want to sort of have one machine that plays the role of two. So union is one case that this might be useful. Intersection is another. Other things that you could do, in fact, this might make a good homework problem. I'll tease it for you then, is if I wanted to do language 1 minus language 2. That's another situation where it might make sense to use a cross-product construction.